Today, we are diving deep into what might just be the future of fish farming, Recirculating Aquaculture Systems, or RAS. This isn't just about growing fish in a new way. It's about completely rethinking how we produce one of the most important sources of protein on the planet.
And let's be honest, that's the big question, right? Our oceans are under a ton of pressure. Wild fish stocks are strained, but the global demand for protein is just going up and up. The old ways just aren't going to cut it anymore. The answer, it turns out, might not be in the sea at all, but on land.
So, let's get into this solution. How do these, futuristic-looking farms actually work? And what is it about them that makes them such a potential game changer for our food security? So, what exactly is a RAS? At its heart, it's a land-based fish farm that basically acts like its own little self-contained world. Instead of constantly pumping in fresh water and pumping out waste, it cleans and recycles almost all of its own water in a never-ending loop. And that gives the farmers total control over absolutely everything. Temperature, oxygen, you name it. Now, when you put it side by side with traditional fish farming, the difference is just stark. Think about it. Marine cages are out in the open ocean, totally exposed. Earthen ponds use incredible amounts of water. RAS just flips that whole script. We're talking about a massive shift from high impact and zero control to minimal impact and total control. It's a whole new ballgame.
And here's the magic number that makes it all possible: 99%. Up to 99% of the water is reused. That is just incredible. That efficiency means you can build one of these farms practically anywhere, in the middle of a desert, right next to a city, completely cut off from lakes or oceans. And that, in turn, slashes the carbon footprint by bringing the fish right to the consumer.
Okay, so if you can build one anywhere, how do you actually do it? What's going on under the hood of one of these high-tech farms? Let's take a look.
The whole thing is built around this constant loop of water treatment. So water flows out of the fish tank, carrying all the waste with it. First, it hits a mechanical filter that grabs all the solid stuff. Next, the water moves into the biofilter, and this is where the real magic happens. After that, carbon dioxide gets stripped out, pure oxygen gets pumped back in, and that crystal clear water heads right back to the fish. It's just a non-stop life support cycle.
You can really think of the whole farm as a living thing, and these are its vital organs. The tank itself is designed so the water flow cleans it automatically. The drum filter is like a sieve, taking a huge load off the rest of the system. The degasser, well, it's kind of like the lungs, breathing out CO2. But the most important organ of them all has to be the biofilter.
And here's why that's so crucial. Fish produce ammonia as waste, and ammonia is super toxic to them. The biofilter is full of material that gives beneficial bacteria a place to live. And these little microbes are the real workhorses of the system. They eat that toxic ammonia and turn it into nitrate, which is way safer. Seriously, without this living kidney, the whole farm would crash in a matter of hours.
Okay, so we get the system, but what kind of fish are we talking about here? It turns out the choice of species is absolutely critical to making one of these farms work.
Now, while you could technically grow a lot of different species, the industry really focuses on the ones where the money makes sense. That usually means high-value fish like Atlantic salmon or Japanese eel. Or it means raising fish through their earliest, most fragile life stages, where the total control of an RAS means way more of them survive. And of course, species like tilapia and shrimp are also really popular for fine-tuning how the whole biological system works.
Which brings us to, the multi-million-dollar question. These systems are incredibly cool and sophisticated, sure, but can you actually make money with them?
Here's the tough part. The upfront cost to build one, the capital expenditure, or CapEx, is massive. You're basically building a biological factory from scratch. And the day-to-day running costs, the OpEx, they're no joke either. You've got life support systems running 24/7, which means a huge electricity bill, plus specialized feed and a need for highly skilled people. That's the core challenge. But, and this is a big but, there are huge advantages that help balance those costs. Take a look at the feed conversion ratio, or FCR. That's just how many kilos of feed it takes to grow 1 kilo of fish. In the perfect, controlled world of a RAS, fish are just more efficient. They have an FCR of about 1.125 compared to 1.264 in cages. Now, that might not sound like a big difference, but when you're producing thousands of tons of fish, that tiny number translates into massive savings on feed. And feed is a huge part of your budget.
So how are operators making it all work? Well, the latest strategies are all about being smart and efficient. People are turning waste sludge into valuable fertilizer, they're adding solar panels to crush those electricity costs, and, critically, they're building big. You really need to be producing at least 5,000 tons a year to make the economics work out. It's all about designing a smarter farm from day one.
And this whole idea of smart design is pushing the entire industry into its next evolution, what people are calling Aquaculture 4.0. The future of RAS isn't just about better pipes and filters, it's about intelligence.
This timeline of patents tells the entire story perfectly. You see, just a few years ago, all the innovation was in the hardware. Better tanks, new filters. Then the focus shifted to mastering the biology inside the system. But today, the cutting edge is all about data. The real value is shifting from the physical farm to the intelligence that runs it.
And that, of course, brings us to artificial intelligence. AI is what's turning these farms from reactive systems, where you fix problems as they happen, into predictive systems, where you stop problems before they even start. AI can see an ammonia spike coming and warn operators, or perfectly time feeding to when fish are hungriest.
And this isn't science fiction. Check this out. A real AI model called Feeding Monitor uses cameras to watch the fish and score how intensely they're eating. It's over 95% accurate. By knowing exactly when the fish are hungry and when they're full, it can cut down on wasted feed by up to 35%. That's a direct, massive impact on the bottom line.
Then you have this incredible concept called the digital twin. Imagine building a perfect, one-to-one virtual copy of your entire farm inside a computer. You can then throw anything you want at it, simulate a power failure, a pump breaking, and see what happens, all without putting a single real fish at risk. It lets you design farms that are unbelievably robust.
And finally, we're getting to the point where we're not just letting the right bacteria grow, we're designing them. This is called microbiome engineering. It's like being a gardener, but for microbes. You actively create a custom community of beneficial bacteria in your biofilter that are specifically chosen to fight off and suppress any bad guys, creating a natural defense system without chemicals.
So we've gone from simple tanks to these intelligent, self-managing ecosystems that you can put anywhere on Earth. As this tech gets smarter, more efficient, and cheaper, it really makes you wonder, is this blend of biology and artificial intelligence the answer? Is this how we're going to sustainably feed the planet? Thanks for watching.